Hello everyone. In this video, we move on to a new section, life annuities. Life annuities consist of a series of benefit payment contingent on the survival of an individual. Here we consider a whole life annuity deal, the discrete case where the payments are made annually. Consider a whole life annuity deal. For annuity deal, the payments are made at the beginning of each time period. And here we have annual payments. So the payments are made at the beginning of each year. The payments amount is 1, depends on the survival of the individual. That is, the individual will receive an amount of 1 immediately. And then if the individual survives to age X plus 1 and other payments of 1 at this time point, the payments continue until the death of the individual. Say at this time point corresponds to the event that Kx equals K. After that, there are no more payments. We let Y be the present value random variable for the aggregate payments. Recall that for insurance, we use Z denote the present value random variable. The aggregate payment, Y equals 1, the first payment of 1, and then the second term due, the present value of the second payment of 1. Altogether, there are K plus 1 or Kx plus 1 number of payments, and this form an annuity deal. So in terms of the notation, this is A double dot and then angle Kx plus 1. How about the expression? Recall the annuity certain. For annuity deal, A double dot angle N, we have 1 minus nu to the power N over D, where D is the rate of discount. And here we replace N with Kx. And so we have this expression for Y, where Kx equals 0, 1, 2, etc. We are interested in the expected value of Y. The actuarial notation for whole life annuity deal, A double dot, and then the age of the individual, X, A double dot X. Here we use 2 approaches to get the expected value of Y. The first approach, we make use of the individual payments. The first payment of 1, the individual will definitely receive this amount because the individual already survived at this time point. So the probability of receiving this 1 is what? And then the next payment, the probability of having this payment, the individual must survive to age X plus 1. The corresponding probability is Px. And then the following payment, the probability of getting this payment of 1 is 2Px. To get the expected value of Y, we multiply the present value and the associated probability and then sum them up. So we have 1 times 1, the first term, the second term, nu times Px, etc. And this equals to the summation of nu to the power K, Kpx. And we can express this expression nu K, Kpx as pure endowment, Kex. Using this approach, the expected value of Y is the summation of pure endowments. The second approach, we will establish the PMF table for Y, and here we will use the probability function for Kx. And Y is A double dot angle Kx plus 1. Starting from Kx equals 0, the individual will receive exactly 1 payment at this time point. The probability of Kx equals 0 is Qx, and the value for Y is A double dot angle 1. And then if Kx equals 1, the individual dies in the second year of the policy. The individual will receive exactly 2 payments. the corresponding probability, kx equals 1, is 1 bar qx, and the value for y is a double dot angle 2. For kx equals 2, the individual received exactly 3 payments of 1, and we have the corresponding probability, and the value for y is a double dot angle 3. All right, so the expected value for y, this is the expression using the proper definition for the expected value. We have the PMF table. We sum up the value of y and then times the probabilities. And we get this expression. And we can express k bar qx as kpx times qx plus k. All right, comparing these two expressions, the second one, we use the proper definition of for the expected value of y. So here we can get a similar expression for the expected y square. And for the first expression, this is a more convenient expression to get the expected value of y. However, we cannot make use of this expression to get a higher moment. Okay, because nu to the power k is not exactly the value of the random variable y, and kpx does not represent the corresponding probability. All right, so we have two expressions. This expression is more convenient to get the expected value. However, to get the expected value of y squared, we must use the proper definition from the basic principle. All right, so the maximum value of y, because this is a form of an annuity deal, so the maximum value of y corresponds to a perpetuity deal, which equals to 1 over the rate of discount, 1 over d. As mentioned, the expected value of y squared, we cannot make use of this. Okay, comparing these two expressions, we simply replace delta with 2 delta in the second expression. So we still have the actuarial notation, okay, the pre-superscript 2 and then a double dot x. However, this is not the second moment. The second moment, the expected value of y squared from the basic principle, the square of the value of y and then times the associated probability. All right, let's take a look at an example. For a whole life annuity deal issued to an individual at age 80, you are given the following life table. The interest rate is 8%. Calculate the expected value of y and the variance of y. All right, in terms of the actuarial notations, we have these notations. All right, the expected value of y denoted a double dot 80, two approach, and we will use the first approach. kpx, given the life table, kpx equals lx plus k over lx, and we need to get kp80. So kp80, we have L80 plus k over L80, and then the present value factor. The first term, k equals 0. So this is simply 1. The second term, P80. P80 is L81 over L80, 100 over 120, and then the present value factor. And then we have the second term, the third term. So we get the expected value of y, which is 2.4702. To get the expected value of y squared, make use of this expression from the basic principle, the value of y squared times the associated probability. The expression for kp80 times qk plus 80, we have this expression. All right, the first term, k equals 0. So we have the value for y, which is 1. This corresponds to a double dot angle 1 with a square. And then the corresponding probability, 20 over 120. We have L80 minus L81, and then over L80. The second term, k equals 1. K equals 1, we have a double dot angle 2, and then the corresponding probability. This corresponds to L81 100 minus L82 70. We have 30 here, and then over L80. To get a double dot angle 2, we can make use of the recursive formula. So this equals a double dot angle 1, and then plus the present value at this time point, which is 1.08 raised to the power minus 1. And we get 1.9259. And then the next term, k equals 2. Altogether, 3 payments. So this value, 2.7833, corresponds to the value of a double dot angle 3. And we can get this from a double dot angle 2, and then plus the present value at time h82 here, 1.08 to the power minus 2. And then the probability, L82 70 minus L83 30, we have 40, and then over L80. And then we have the last term. All right, so this is the expression for the expected value of y squared. Upon calculation, we get this quantity. To get the variance of y, make use of this expression, and we get the answer, 0.7733. All right, another example. For a whole life annuity deal issued to an individual at age 5, given that S of t, the survival function, is 1 minus t over 10, t is between 0 and 10. I is 0.05. The annuity payments, a benefit of 20 at the beginning of the first year, 35 at the beginning of the second year, and $50 thereafter. Calculate the actuarial present value of this annuity. Let y be the present value random variable for the annuity, the time diagram. And here t is between 0 and 10. So that means we have the limiting age, omega equals 10. And then the corresponding payments. The expected value, or the actuarial present value. All right, so we have the payment other than 1. So we make use of the notation BK. BK corresponds to the payment at age, say, x plus k. So the present value is pk times the present value factor nu to the power k. And then use the more convenient expression. Multiply this present value of the payment by kpx. And here the individual is at age 5, so we have kp5. So kpx, we have this expression. We need to get kp5, omega 10, x is 5, and nu is 1 over 1.05. All right, we get this expression. For k equals 0, we get 20, and then the probability 0p5 is simply 1. The second term, the payments is 35. The present value is 35 times nu. The corresponding probability, P5, k equals 1. So we have 4 over 5. Upon calculation, we get the expected value of y, 99.38. The variance of y. Okay, recall that we cannot use the more convenient expression to get the higher moment. So the expected value of y squared does not equal this expression. Therefore, we need to build up the PMF for Y. All right, Y equals 20. That is, the individual dies before reaching age 6. The corresponding probability is 1 minus P5. And we get the expression for the P5 here. So the probability is 1 over 5. And then if the individual dies between ages 6 and 7, the individual will receive a payment of 20 at this time point and the payment of 35 at this time point. The value for Y, the present value of these two payments, 20 plus 35 times nu. The corresponding probability, P5 times 1 minus P6. And then if the individual dies between ages 7 and 8, the value for Y, we have this expression, and then we can get the corresponding probability. Okay, fill out the rest to complete the PMF table for Y. All right, for the probability, you can see that the probability are constant. Okay, because with this expression KPX, this simply is the De Morphius law. So we have KP5 times QK plus 5, which is 1 over 5. All right, doing the calculation, we get the PMF table. With this table, we can get the expected value of Y and the expected value of Y squared. And then we can get the variance. And this is the answer for the variance. That's it for today's video. Thank you for watching and see you in the next video.